So how did ODP 214 work? No major issues. Basically just add the square of the probe before you reduce. All right, yeah.
So what does the probe do?
So the idea of probing is you have a hash table and if you're not doing like we're doing in our programming assignment where we have linked lists, if you're just storing your data in the hash itself, you run your hash function with a key and it gives you a location and says store your data there. If that location is in use, right, that's a collision, something's already in that spot, you need to find another spot to try to store your data. So you rehash with a probe of 1 instead of 0. You get a different location from the hash function. So it's like an attempt number. So you hash attempt 0, it gives you an initial location. If something is already there, hash another time, right, with a probe of 1, and maybe that gives you another location. And if there's something there, hash with a probe of 2. Maybe that gives you this location, and that's empty. That's where you can store. So it's a way to rehash, to say, well, if that didn't work out, let's try again. Give me another location where I could try to store this in my array. With chaining, PA3, we don't have to do that because we're not actually storing in the array. This is just telling us where a linked list is, and we can add as many things to a linked list as we want. Right, just keep inserting new nodes. If we're actually storing in the array, there's exactly one thing that we can store in this location. And so once we've stored something there, there's no place to store anything else. So we have to find a different spot to store. All right. So let me just run through a version of PA2 that I coded up. This is all in one file instead of being modularized. But it's basically a translation of the one file version from PA1. Your struct node is as usual function prototypes, which were specified in the assignment. I still have my usage function, which tells the person legal commands, and my process function, which does everything that the user wants done. My linked list is called list, right? And it starts off as a struct node star, which I initialize by calling a init, and buffer is just my usual temporary character array. So print a prompt, call fgets to read a line of input from the user, and if that returns null, the person hit Control D, so I'm going to exit the program. Otherwise, process the buffer. Process needs to know the linked list as well so that it can make changes to it and examine it. And then process returns a 0 if the person said exit. So if process returns 0, I'll exit here. Otherwise, I'll print a prompt, go back to the top. So that's exactly the same as the previous version. And process should be exactly the same also. Let me... So here's PA1. So same prototypes, main function is exactly the same. Process function is exactly the same. So it's just a wrapper around the calls to search and delete and print and so on and so forth. Help message usage code is the same. Let's look at init. So init for PA1, right, we set up the sentinel to point to null, and then set all the other entries in our array to be valid. for PA2 init, all we have to do is call malloc, set the next field of that node to be null, and return that node. So that's actually a little simpler. And then the add function. So pair of pointers, previous and current. Previous starts at the sentinel, current starts at the first data node. Oh, that's interesting. That's sad. Okay, so no segfault possible. All right, previous is the header node, current is the first data node, and we know that always exists because the sentinel always points to something. So previous next will not throw a segfault, but current could be null. Okay, so we're going to iterate while current is not null. First, we're going to make a new node. If malloc returns null, we're out of memory. Otherwise, we set the new node's data field equal to num. And this is what we were doing over here, right? Previous is sentinel, current is the thing that the sentinel points to. Call get node instead of malloc. If it's null, we're out of memory. Otherwise, set the data field of our new node to num. So one thing I saw in a few spots was this. Right, I saw this pair of statements pop up. The first is calling malloc to see if malloc returns null, because if malloc returns null, you're out of memory. But if it doesn't return null, you're not out of memory, so then the person calls malloc to get a sentinel node and saves that in this variable sent. This is a guaranteed memory leak, right? Because when you call malloc, yeah, you're checking to see if you're out of memory, but you're also allocating a block of memory. Okay, which will need to be freed at some point, but you didn't save the address of that block anywhere. And when you call malloc, you're allocating a new block of memory, and you're not checking to see if that's null. So you got sort of three issues going on here. Really, the way to do this is try to allocate a block of memory for your sentinel, and then check to see if that's null, and if it is, you're out of memory. Otherwise, just continue. So if you do this, that's a memory leak. And this you might run out of memory and not realize it. Does that make sense? Right, every time you call malloc, you're allocating memory. So you can't just call malloc to see if there's memory left, because you're also allocating memory in the process, which might use up your last piece of memory. All right, so call malloc, see if it returned null. If it did, return out of memory. Otherwise, set the data value. And then move down the list. So do this while your current node is not null, which means you haven't run off the end of the list. And it's the same drill as before. So if the current data is bigger than num, you're going to insert between previous and current. Otherwise, move down the list. So if current data is bigger than num, have the previous point to your new, have your new point to the current, and you're done. Otherwise, set previous to current, current to current next. If you come out of the while loop, you're at the end of the list, you want to insert after previous, right? Not after null, after current, because current is null. So you want to add your new node after previous. So previous next is new, and then new points to null. All right, print is exactly the same. It's just current arrow data instead of list bracket current dot data. And then delete, same pair of pointers, previous and current. And again, I'm starting off previous at the sentinel, current at the first data node, or null if the list is empty. Okay. So while the current node is not null, see if that node's data is what you want to delete. I'm never checking previous data, which means I'm never checking the sentinel's data. Okay, I'm starting with the first thing that the sentinel is pointing to. And if that's equal to num, then how do I remove current, have previous next point wherever current next is? Okay, this is a critical operation here. You might see something like this on the midterm. Here's previous, here's current. How do I delete that current node? I want to change this to point over here. Well, this block that I want to change, that's just previous next. And I want it to be the address of this node. Well, I can find that address because current is pointing to that node. So I said previous next equal to current next. That sets up that hop across current, and then you want to free this current node, so just free current. And that's a good deletion. So all the work is moving down, figuring out where the node is that you want to delete, and making sure that previous is the node right before, so that we can make that adjustment. All right, and then search is just traversing down the list, current equals current next, until current data equals num, in which case you found it, or your current node is null, in which case you hop out of here and say I didn't find it. And then releasing all of the memory. Here I'm starting with the sentinel node because I want to delete the sentinel as well as all the data nodes. So I've got a pointer which starts off at the sentinel. I've got a temporary called free this. And while my pointer is not null, I set free this to the thing I'm about to free. And I move the pointer to the next node. So here's PTR. This is also free this. Change PTR here so that I can keep moving down the list and then free this. And then go back to the top of the loop. Pointer's not null, set free this equal to the node I'm sitting on right now. Move PTR, free this. Back to the top of the loop, still not null, so set free this equal to here. Set pointer to the next node, which makes pointer null. And then free this. Back to the top of the loop. Notice that pointer is null. Don't try to free anything else. You're done. You're at the end of the list. So when you kick out of your loop, you just return from the function. So 174 lines versus 189. I think I had more comments in PA1. Does that make sense? So edge cases are always a little tricky. All right, should I start at the sentinel or sentinel next? Should I stop when I'm null or when current arrow next is null, and so on and so forth? Work through, examples with sentinel and 2 or 3 nodes and nail down the edge cases. And the rest of it is just pretty mechanical. All right, so there's my hash function for ODP 214. I just initialized sum to the square of the probe instead of adding it at the end. So it was really just one line in the beginning. But there's different ways to do that. All right, so any questions on PA1, linked lists, pointers, dereferencing pointers? So let me mention a couple of other options for linked lists. A lot of times when we're doing things with lists like trying to delete or trying to add, we need to keep this pair of pointers so that when we get to the spot where we want to do something, we know what the previous node is, right? There are ways around that. One is to use what's called a doubly linked list. And DLLs are very convenient. So our nodes have an extra field. And it's typically data. And next as usual, but we also have a pointer to the previous node. And so this is our sentinel. Our next node points here. Here's our first number. Next points there. There's our second number. There's our third number, and next is null. But we also have these back pointers, which point to where you came from. Well, and I'd probably make the first one null, even though we came from a sentinel. Okay, this is nice because if you want to delete a number, let's say we want to delete the number 20, start with a node the sentinel points to. Is that 20? No. Is that 20? Yes. As soon as we know that that's the node we want to delete, we can find the previous node because it's just this node's previous field. Right? So if we think of this as, you know, this, how do we delete this? Well, we want the previous node's next field. Well, the previous node is this arrow previous. We want that thing's next to be equal to whatever this is pointing to, which is this next. So that sets up this link here to point to the 30. And then we need to change 30's previous to point not to the 20, but back to the 10. So the node following this is this arrow next, and we want that thing's previous to be equal to this node's previous. And that sets this back pointer up to point all the way back to the 10, and then we can just free this. So the lines are a little longer, but the processing is a lot simpler because we don't need a pair of pointers. And if we want to insert right before this node, it's the same thing. Right? Make a new node, have this arrow previous, arrow next equal our new node, have our new node equal this. Have this previous equal our new node, have our new node previous equal this previous. Don't ask me to say that again. Right? But this is good exercise for matching the algorithm with the pictures with the code, right? I will write that out. So let's say we want to insert a node here, insert a node new right before the node here. And let's just remember this is data. This is next, and the last field is previous. And here's our new node. Alright, so how do we insert new right before here? Someone give me a line of code that will help.
Do you want news next? You want yours previous?
Just one line of code. new next is equal to here, so this is new next. That's going to point right there. Okay, somebody else, give me a line of code, because we got a few lines we can write here. Yeah. New arrow previous arrow next is equal to new. So new previous, yeah, new doesn't have a previous yet. Here previous, good. So here previous is this node, arrow next is equal to new. Awesome. Now the node before here is pointing to new. New is pointing to here. We've got our forward chain set up. All right, somebody else.
New arrow previous equals here.
New previous equals here previous. All right, new previous is going to point to whatever here was pointing to, while our back pointer from here should have been pointing to this node. So we're setting up new previous to point here. That looks good to me. Awesome. All right, one more line of code for fame and glory. Let me add some data values. I'm assuming this is sorted. Sure. Well,
That's the same thing as here.
yeah, right here.
No, we changed that field.
Yes, that will work. So here, arrow previous, that's the backlink from here, is equal to here, arrow previous, while here so far is pointing to the 10, and if we follow the next, that'll point to the 20. So that will set the previous of this up to here. Awesome. But as you were just noting, here previous next, we already set that equal to new. So we could also have just set this equal to new. It's exactly the same thing. Cool. All right, so inserting into this is a little more legwork, right? But basically, node 10 points to a 20, node 20 points to a 30. If we follow the back pointers, 30 points back to a 20, 20 points back to a 10. Okay. If you draw the pictures and that works, then you know your code is right. Right? You can write the code and test it with pictures, or you can write the pictures and jot down the code that corresponds to what you're doing. Whatever works. So doubly linked lists are nice. The nodes are bigger. They have an extra 8 bytes usually for the back pointer, and they take a little more maintenance, but they simplify the processing in terms of not having to keep a pair of pointers when you move through, and they can clean up some edge cases maybe as well. So doubly linked lists are useful. The other thing you'll see sometimes is a circular list. And if you, with a circular list, the last node in the list, instead of being null, just points back to the first node. And I'm not drawing a sentinel here. Assume it's just a list of nodes. The last node points back to the first. And that can be useful for a few reasons. One of them being that maybe the things that are in your list are things that you want to process again and again and again. For example, these might be jobs that an operating system is executing one after the other. And so you make a circular list of jobs and you move from one to the next to the next. When you get to the last job on the list, you want to go back to the first job again. Well, there's no special case here. You don't have to say if the next field is null, then set my node to the first node, right? You just keep following the chain and you'll go through it forever. On the other hand, if you wanted to print the contents of a circular list, you got to do some work. You can't just print until you get to null because you'll print forever. So typically you have to do something like notice the address of the first node and then keep printing while the address of the node is not that first address. And you got to start the process somehow.
When you didn't draw the sentinel, is that usually outside the circle, or is it in the circle?
I think it would be outside the circle. It's a way to get to the list, but it looks quirky. But you could have the last node point back to the sentinel. But then every time you get to that, you have to know not to deal with that node's data. So. And you can do circular doubly linked lists for bonus fun. So there's all sorts of variations on this.
What would be an application of a circular list?
Process queue is the one that comes to mind usually, right? So these are processes that are being executed. And, you know, new processes may be inserted into the queue, or into the list, so that when you get to the end, you come back. Now that's part of the round robin of process execution. We're going to talk about stacks and queues next, which is actually where we do process management. All right, well, what happens if we don't have a sentinel? Suppose for some reason we don't want to have a sentinel node in our list. And sentinels are odd. I mean, they're this node that's sitting there, but they're not actually a node. We've got to ignore the data. If there's no sentinel, then an empty list is just null. There's no nodes. If there's a list with one element, it looks like this. Data and null. If there's two elements, there's a data in the first node, it points to a second node, there's data, and that's null. So if you have n elements in your list, you have n nodes in your list. So if your list has no elements, your list can contain no nodes, it's null, right? That works fine except when you try to code it. So let's do add. So let's look at code for adding a number to a list. And let's just say we want to insert in the beginning of the list. Okay. And this is with no sentinel. Well, in general, right, we can just do the following. We can say, with a sentinel, we just have the sentinel point to the new node, have the new node point where the sentinel was pointing. Okay. If we don't have a sentinel, let's suppose that our list looks like this. Right, list is a pointer to the first node of our list. If we want to add a new number to the beginning of this, right? Well, we're just going to make our new node, and that's going to point to list. But list now needs to change and point here. In other words, we need to change the value of this argument that was passed to us. And we can't change the value of an argument in general because arguments are passed by value. The address that's passed to add is just a number. If I change list inside here, that number doesn't change value. When I get back to the caller, that argument has an unchanged value to it. So you've got a few options. You can actually pass a pointer to the address of the sentinel. So you would pass ampersand list, right? And then in here I could say star list equals, right? That's a little quirky. So typically what we'll do is instead of making this function add, we'll actually make this function return a struct node star. So it returns a pointer to the list's first node. So if you want to add a new node to the beginning of the list, right? Bless you. Right, Malika struct node star new. Set its data field equal to the number that you want to save. Set new arrow next equal to list. So this new node points to the address of the node that was passed in. But we want this to be the new start of the list. So we'll say return new. And whoever calls this has to do the following. You call the add function, you pass it the pointer to the first node, you pass it the number that you want to insert, but you take the return value from add and you change list to be equal to that. So inside add, list is the second node of the list, new is the first node. We return new. Up here we're going to say list equals new. Well, now we've done this. We've set up list to be the address of that first node. Yeah?
Could you also just change what's stored in the list and then move whatever was there into a new
You can do that, but usually we don't want to do that. If it's just integers, it will work. But if this is something that's, you know, a few thousand bytes of information, we don't want to start moving these things around, and sometimes it's multi-levels, and we need to actually write a loop to move all the data pieces. Effectively, yeah, we could just make a new thing, change list to 5, have the new thing be 10. That would get us there in the end, but that's a special case when you're able to do that. All right, so we end up doing this for add, we end up doing it for delete, right? Anything that might potentially change the beginning of the list, we have to be able to pass that new beginning back to the caller. And in the case of delete, right, if our list consisted of just a 5 and we wanted to delete a 5, our list in our main program has to change from the address of this node to just being null, right? And so if we delete and we return a null from here, right, our main program can set the list to be null. But it's also an edge case, right? We need to know that we're not going to return the address of the thing before this. We're going to return null, right, because there is nothing before that. So the Sentinel nodes clean up sort of the logic of the code and some of this special handling. But in some cases, we won't bother with a Sentinel. And when we talk about trees, which are really a form of a list, we will never use a Sentinel node. for various reasons. But keep them for now for PA3. All right, we got 10 minutes. We're starting something new. Let's talk about stacks. So how many people have taken Engineering 270? Most people, okay, so you've dealt with a stack, but maybe not sort of grokked the whole concept. So what is a stack? A stack is a collection of numbers, let's say, and you can say, here's a number, save this for me, here's another number, save this for me, here's another number, save this for me. It's a thing that you can throw numbers into, and they will save all these numbers for you, and you can get them back later. You can say, what was that number I gave you? What was that number I gave you before that, right? So it's generally a structure into which we can toss numbers and we can pull numbers back from, okay? But it has a very peculiar or very particular way of saving things and giving them back to us. And the acronym we can remember is FIFO, which is first in, first out. No, it's a LIFO. Erase your last 15 seconds of. So it's last in, first out. Okay, what does that mean? The last piece of number that you threw into the stack, when you say, give me a number that I gave you, the last one you gave it, that's the first one it's going to give back to you. So I say, let's remember a 10 and a 20 and a 30. And now I say, give me back a number that I asked you, it's going to give me back a 30. And if I say, give me another number that I gave you, it's going to give me my 20. And if I say, give me another number, it's going to give me my 10. And if I say, give me another number, it's going to say, there are no more numbers. Okay. Now if I give it a 10 and a 20 and a 30, and I say, give me my last number that I gave you, it'll give me back my 30. Now if I say, can you remember a 25 for me? And I say, what's the last number I gave you? It'll give me a 25. Give me the last number I gave you before that, that's a 20. If I say, go ahead and remember a 55, and remember a 65, and now I say, give me the last number, it'll give me 65. What's the last number before that? 55. What's the last one before that? 10. Yeah?
Is there any way to put the specifications on what the last thing that you,
It's,
what you want back?
it's always the last thing you put in.
Always?
Yeah, for a stack, it's always.
Give me the last thing that the modulus of 5.
No.
Okay.
You can just pop and just throw them all away.
You could pop and throw them all away, but if you wanted some of those other things, they'd be gone.
Can you pop them all, put them into a different stack, and then?
You can implement what you're asking for, absolutely, right? But on a straight stack, no, it's always just give me the top thing from the stack. But yeah, you can definitely do that. And there's times when you would want to do that. All right, so it's a last in, first out, or a first in, last out, but it's always called LIFO instead of FILO. So last in, first out. Okay, so where does this pop up in life? Here's the way I learn stacks, okay? Go into a Chinese restaurant, go up to the buffet, you grab a plate, right? There's a pile of plates there. And there's this cool little cart, and it's got wheels, you know. And there's plates sitting in there. I am not skilled at drawing plates. Those look more like bowls. And there's a spring down here, spring-loaded platform. Okay? You always take the top plate. You can't take the plate below it unless you take the top plate first. So you look at the top plate and it's all wet and you don't want it. Well, you got to take it off to get to the next plate below it. Okay, you always pull off from the top of this stack. So this is like a stack of plates, and this is the top of stack, which is usually called TOS. We're firing 270 neurons now. That's the top of the stack. Okay. You take that plate, this plate below it moves to the top of the stack. You take that one, this plate moves up. You take that one, this one moves up. If you take that last plate, now there's just a platform sitting there. And if someone says, hand me a plate, there are no plates, the stack is empty. Okay. If you try to take a plate from an empty stack, that's called a stack underflow. Okay, so underflow, which is taking from an empty stack. And the word we use for taking something from the stack is pop. So popping means remove from the top of the stack. Putting something on the stack, the word we use is push. So pushing is put on top of stack. And so every now and then the dishwasher comes out from the back and is carrying a big set of plates, right? And what do? You take the plates and you put them on the top of the stack and everything moves down. Put a plate, put another plate, put another plate. 10 plates get added to the top of the stack. The next person who comes to the buffet, what's the first plate that they're going to get? The last one that the dishwasher put on the stack, right? And that one's all wet and everything, and so they don't want it. Well, they can't get to the one below it until they take that one off and hand it to the person behind them very politely. And then they take the dry plate. Okay, so that's the same mechanism that we have in a computer stack. It's the same mechanism we have in the structure we're going to be talking about. You always insert at the top, you always remove from the top. Okay, insert is a push, remove is a pop. The other thing that can happen is you start putting plates on here while this spring gets compressed more and more and more until there's no more room for us to compress. The plates are stacked up all the way exactly at the top. And now what happens if someone comes along and tries to put another plate on top? It's going to fall off, right? That's a stack overflow. So an overflow is trying to add to a full stack. So overflow happens when you try to do too many pushes. Underflow happens when you try to do too many pops. Okay, so we got a push, we got a pop, we got a top of a stack, we've got an empty stack, we've got a full stack, we've got underflows and overflows. I think that's it for terminology. And the whole thing is a last in, first out. Okay, why do we care about stacks? Other than eating a Chinese buffet. It turns out stacks are central to not just computer science, but actually a lot that we do in life. So here's a scenario. So let's say you're doing your homework. You're doing your physics homework. And while you're working on your physics homework, you get a message on your phone from a friend. Okay, and your phone beeps. Okay, you want to stop working on your physics homework and look at your phone and see what's going on, right? So you don't throw your physics homework away and say, forget this, I'm going to go talk to my friend, right? You leave it on the table, right? You put a bookmark in your book or something like that, and now you check your phone. And the idea is when you're done checking your phone, you're going to come back to where you were on your previous task, which was doing your physics homework, problem 7 or whatever. Okay, you check your phone, and it's your friend saying, hey, you want to get some lunch? And you say, yeah. So now you're going to get lunch. And while you're out getting lunch, you realize that you're almost out of gas. So on the way to the lunch place, you have to stop and get gas, right? And what you're doing is you're populating your mental stack with tasks. I'm getting gas, but when I'm done getting gas, am I going to go back to doing physics homework? No, I'm going to continue getting lunch. And while I'm on the way to lunch, I'm going to say, oh, I forgot I need money. You're going to stop at an ATM. And when you're done with the ATM, you're going to go back and continue getting lunch. Right? So every time that we're doing something and we want to do something else, we sort of take our current state and we push it on a mental stack. Okay, I got to remember to get back to my physics homework, but I'm going to have lunch first. And while you're at lunch, it's like, oh, I gotta get gas, but I gotta remember that I'm going to get lunch, you know? So you push your lunch on the stack and you get gas and drive further, and oh yeah, I need money, so you go to the ATM, you put lunch back on the stack, and when you're back from the ATM, you go to the lunch place, and now you can pop this from your stack and eat lunch. And if nothing else goes on your stack, when you're done, you can go back to doing your physics homework, right? But maybe after lunch, it's like, oh yeah, let's go to the movies, right? So you put that on your stack. And this is how we get through our days, right? And it's usually a stack-based behavior. I mean, the other option is, you know, I'm doing physics homework, your phone makes a noise, well, I'll check it after I'm done with my homework. You finish this task, now you check your phone and it says, oh, let's get lunch. Okay, so you go to get lunch and you run out of gas on the way. It's like, well, I'm still going to eat my lunch, right? And then after you finish eating your lunch, you walk back to your car and you get gas, right? That doesn't really work for life. Mostly we operate on a stack. And same thing when you're surfing the web, right? You're looking up Maxwell's equation, and while you're browsing that, you see something that catches your eye, so you click on it and you go to another page. And you see something there, and you click on that, and you go to another page, and it says proof that aliens exist, and you click on that and go to another page, right? And when you're done with that last diversion, you're going to hit the back button and go back to the page you were on right before that, and keep reading it, and it's like, oh, sports scores, and you go off on that, right? And eventually, after you go back enough, you'll end up back on Maxwell's equation, right? And read the second paragraph and continue. And this is how computers work too. This is how they deal with interruptions to what they're doing. Here's a network packet, here's an email message, oh, the clock just updated, this person just clicked the mouse button. These things are handled with stacks. All right, so we'll talk more about stacks tomorrow. We'll talk about implementing stacks. Stacks as abstract data types. We'll move on to talking about queues after that.